All right, so we're going to talk about linear algebra today. The main things we're going to talk through, why linear algebra, it's a very math thing. I will say that like in college, you take an entire semester of linear algebra where we literally have one day on it. So I will highlight why, like what part of it is going to be important for us as data scientists as we get through it. Why linear algebra, how we use it, what are some of the data types. We're going to work on some operations with vectors and matrices. We'll talk about linear equations, which I think is kind of like a good lead up to finally one big use case of linear algebra is solving linear regression, which I'm aware is your phase 2 project that I think you're just about finishing. Actually, the stats models package of linear regression uses linear algebra to solve for the coefficients versus to contrast to scikit-learn's package, which I think you also used, does a gradient descent procedure. So there, if you ever notice like some of your coefficients are a little bit different, that is why. But to start, why linear algebra? So linear algebra is the basis of many machine learning models, mostly because you're thinking in multiple dimensions. Whenever I think of linear algebra, the first thing I like to think about is we're thinking in many different dimensions, and I'll talk a little bit more about how that exists with real life data. So by default, a lot of data is sort of set up like a matrix. I'm going to go into data types, but matrices are basically anything 2D, anything that comes in like a rectangle shape, that's pretty much a matrix. So data is already set up like that. In later stages, I'm going to talk about some of the applications. You'll see that when you get to NLP, a lot of modeling like meaning of words, things like context and semantics can be embedded in vectors, which you would use linear algebra to understand. Images. This is also something that you'll talk about in phase 4. Every single pixel is a value in a matrix. And when you have multiple colors, you'll have like, if anyone has heard of like RGB in like images, it's actually like a red matrix, a green matrix, and a blue matrix layered on top of each other to make all of your colors. So when you get to the image data processing, you'll see that a lot of your information is stored as matrices or tensors, which I will talk about in a bit as well. My personal favorite recommendation engines, the top performing models for recommendation engines actually use linear algebra theory to solve. So it's really interesting. And you'll get to that in phase 4 as well. Finally, I think this is a funny meme that I found. You all just did your linear regression project, but I feel like the way that this is structured, you kind of do the linear regression before getting into like the deep weeds of statistics, linear algebra, and multivariate calculus. So this like step over all of these foundations to get to building your linear regression model. It's good to know what you were doing in the back end. Cool. Well, to start, some data types for linear algebra. So the 4 main data types that you have in linear algebra are scalars, vectors, matrices, and tensors. I think this is a funny graphic because the dogs are the shapes. But scalar, you can think of as just a single number. Any constant number is a scalar, just represents some magnitude. Next, with vectors, vector is an array that has both magnitude and direction. So one way to think about it, and I'll draw a picture in a sec, the coordinates of a vector represent where the tip of the vector would be if you traveled from the origin, and the magnitude would be its length in space. So if I were to draw a picture here, so let's say I have a 2D vector going on, and let's say this is my x-axis and this is my y-axis. Let's say I had the vector 2, 3. So let it just be a 2-element vector. With the vector 2, 3, and let me just get the right drawing up. All right, so 2, 3, let's just say the first one is x, second one is y. 2, 3 means that, all right, we're going to move 2 in the x direction and 3 in the y direction. This is 2, 3, if you look at it as coordinates. But a 2, 3 vector is something that looks like this. So this arrow is a 2, 3 vector. So this is the direction is 2, 3, and the magnitude is literally the length of this arrow here. which you can solve with Pythagoras theorem if anyone remembers that. So yeah, we'll get into that in a little bit as well. Next, we have matrices, which is basically a bunch of vectors together. It can be interpreted differently in different contexts, but it's often used to represent multiple simultaneous vectors. And we'll actually talk about this in the context of like a linear regression data set later on. And then a vector or matrix can be multiplied by a scalar to create a change in scale and or direction. And finally, tensors, which are the example I use is like images when you have an R, G, and B matrix. Tensors are just made up of matrices with the same dimensions. With these data types, just good to be familiar with the names. If someone ever brings up the word tensor, you'll at least know what they're talking about. So something that's important to note is that vectors, matrices, and tensors are represented by NumPy arrays, not lists. We'll see some functionality that NumPy arrays have that lists do not. And then something else that we can use is NumPy array.shape to explore dimensions of these data structures. So this next section, I'm just going to go over some quick examples of all of these data types. So scalars are just numbers. So we'll talk about some vectors, matrices, and tensors. So here, let me just run this cell real quick. You can see here I'm doing NumPy array to make sure that these are arrays and not just Python lists. And these are just some examples of vectors, 2 matrices, and a tensor. And similar to your data frames where you can do like dot shape to find out the dimensions, you can do dot shape to figure out the dimensions of any array. So here you can see that you have a length 6 vector, a 2-3 matrix, a 3-2 matrix, and a tensor here. I put this cell here just in case any of you have this notebook. You can mess around with indexing a tensor. It gets a little bit confusing sometimes, but yeah, you can multi-index it. So multi-index, yeah. So let's say I wanted to get the number 6 out. I know it's in the index 1 matrix. And then next I would have to go, I think, the first row of the matrix. And then hopefully I'm right. There we go. Yeah, it's something that I think, will get used to as you play around with it. Something else I mentioned, the magnitude of the vector earlier when I drew that diagram with the arrow. It's the length of the arrow. In 2 dimensions, it's easy. You can use your Pythagoras theorem to figure it out. Once you get to multiple directions, and imagine you have like a 3D space and you have an arrow pointing somewhere in 3D space. And in most cases, you're going to have more than 3 dimensions that you're working with. Your arrow, you cannot even visualize where that arrow is pointing, but you can still calculate the magnitude. Thankfully, there is this function that does it for you. So np.linalg.norm finds the magnitude of the vector. It actually uses, yeah, pretty much the generalized form of the Pythagoras theorem. So just be aware that this exists to find the magnitude of any vector. Cool. Oh, again, feel free to interrupt me at any point. I prefer being interrupted for questions rather than like stopping and like asking for questions. Cool. Next thing to be aware of is the transpose function. This will come back later, so remember that this exists. But calling transpose on an array just reverses its shape order. I like to think of it in a matrix format. You're just like flipping it across the diagonal. So the rows become columns, columns become rows. This is actually pretty useful for a lot of linear algebra things. Also can be useful in like data frames if like your columns are flipped. I think there are some like there are some CSVs out there that exist in like just weird formats that you have to use transpose on anyways. So know that transpose exists and it does reverse the shape order. You can also transpose a tensor. Very, very rare that you would have to do this, but this I have here just to demonstrate that it reverses the shape order. If I start with this tensor, you see these numbers running from 1 to 24. Transposing it, it goes from 243 to 342, and the numbers get kind of jumbled up. It will also take me some time to rearrange a tensor transpose, but just be aware that it reverses its shape order.
I had a quick question just about like tensors. Like, is it essentially just like a matrix within a matrix?
I would say not a matrix within a matrix, but think of it as like a collection of matrices of the same dimensions. So technically it's a list of matrices, if that is more helpful.
Oh, yeah, thanks.
Yeah, so in this tensor here, we have this first matrix and then this second matrix. So you could think of it as like a list of matrices. I think, yeah, not a matrix within a matrix. I think that would be like a 4D. I don't know. All right, that's a good clarification. All right, really quickly, some operations on vectors and matrices. So we'll start with addition and subtraction. For addition and subtraction of vectors, matrices, and tensors, as long as the dimensions are equal, the operation will occur element-wise. So that just means that if I have this vector here and this vector here, if I take the sum or if I find the difference between them, you will do it element-wise. So you can see here, if I have v, let's start with plus first. So if I have v being 2, 4, w being 3, 2, if I add them together, it becomes 5 and 6 because we're only adding the elements by their index. V minus w does the exact same thing, just it minuses. So 2 minus 3, which gives you -1, 4 minus 2 will give you 2. So this is pretty straightforward. Next I want to talk about is broadcasting. I don't know, is anyone aware of broadcasting? Yeah, okay, that's fine. Broadcasting is, I think, what differentiates a NumPy array from a Python list. You'll see with broadcasting, it actually makes, it's computationally faster, and it kind of makes doing things repetitively. Instead of doing things as a loop, you could essentially broadcast them. So as an example, oh, actually, let me explain it first. So broadcasting happens when you perform operations across arrays with different number of dimensions. So what is happening, and I'll explain this as examples later on, NumPy will make a duplicate of the lower dimension array as long as the higher dimension array contains the same shape to execute the operation. So as a quick example, let's just say that I have the scalar 4, and I have this vector 1, 2, 3, 4, 5, 6. What's happening here, if I do vector plus scalar, I don't have to run a loop or anything. I can just do vector plus scalar and it automatically broadcasts. So it broadcasts the +4 onto my vector, which can be very, very useful. You don't have to loop through and say for every element +4, but it just automatically will broadcast, which is very neat. So this is what I mean by it makes duplicates of the lower dimension array. Again, as long as the higher dimension array contains the same shape. And I'll use another example to show you when this does not work. So here I have a matrix vector example. Here you can see I have this matrix of 1, 2, 3, 4, 5, 6, this vector of 1, 0, 1. If I do m1 minus v1, let's print this out, you can see that this 1, 0, 1 is being broadcast across the 2 rows of this matrix, which is pretty neat. Again, I don't have to do a loop. And it's also actually computationally more efficient. Something that wouldn't work is, let's just say I rearrange this such that it becomes a 3, instead of a 2, 3, it becomes a 3, 2, or did I say it the wrong way around? I forget. But anyways, if it looks like this, in this case, it wouldn't work because it literally will tell you it cannot be broadcast together. So just something to keep in mind, limitations of broadcasting. But broadcasting is very, very neat, very, very useful. Actually, pandas, a lot of pandas operations make use of broadcasting as well. So things like dot apply, if you're applying a function, or if you're just like adding to like columns of a data frame, they're actually using the same broadcast technology. Yeah. All right, so question for you all. I have Tensor 2 over here. Any thoughts on what kinds of shapes can be broadcast onto Tensor 2? I forgot to mention, I like to be a little interactive with my lessons, but does anyone have any thoughts? Feel free to use the chat if you want to speak up. All right, let's go with some like yeses and nos. Let's say this Tensor 2 has a shape of, let's just take a look at the shape, 2, 4, 3. So let's say I have a vector of length 4. Will that be able to be broadcast across this tensor? I see some head shaking. Technically, yes, you cannot, no, technically no, you cannot broadcast a vector of shape 4. Because if you look at the vectors that are contained in this tensor, every vector is length 3. Where the 4 would come in is if I have a matrix of this shape, I can broadcast the matrix onto the tensor. Hopefully that clarifies it a little bit. But feel free to mess around with this if you have this notebook. But yeah, very unlikely you'll be working with tensor operations. Just wanted to point out that broadcasting is extremely powerful. All right.
Can you broadcast the scalar onto the tensor as well?
Absolutely. Absolutely. If I do tensor 2 plus 2, it will broadcast it across. That's right. Awesome. I think I can also show an example of broadcasting this. I would have to do pi.array. And that broadcasts 1, 2, 3 across it. And then I don't want to type out a matrix, but the matrix would work. All right. The next thing we're going to talk about is multiplication. And there are actually 3 different kinds of multiplication when it comes to linear algebra. I'm going to talk about 2 of them. The third one, I'll allude to what it is because you all don't need to know that. The first kind of multiplication is Hadamard product. You very unlikely will use this. Basically, it's element-wise multiplication. So for example, if I have 2 matrices here, same with vectors, the Hadamard product would just be multiplying each element, same as we did for addition and subtraction. So for NumPy arrays, you can just use the star symbol or the asterisk to do the multiplication, just as if you're multiplying like numbers together. So here, when that's done, you can see it ends up as 3, 8, 5, 18, because 3 is, let's see, 3 is 1 times 3, 2 times 4 is 8, 1 times 5 is 5, and then 2 by 9 is 18. So element-wise multiplication is the Hadamard product. One that you will come across more often is matrix multiplication. This is something that is pretty complicated to explain exactly how it works. I will say I have actually gotten interview questions on like, multiply these matrices. Was not expecting that, but just good to know that it has come up as an interview question for me in the past. But basically, if you have 2 matrices, the way that you do the multiplication is you're taking the rows of the first matrix and do an element-wise product with the columns of the second matrix. So I know that sounds kind of confusing. So let me zoom in and we'll sort of break this down a little bit more. So in matrix multiplication, the order actually matters. Whether you're taking A times B or B times A, your result might be different, or it's likely to be different. Ooh, let me just double check. Oh, cool. I just saw the chat. All right, so let me draw out some of this to make it a little clearer. So what we're going to do is you always take the rows of the first matrix. So in this case, we're taking these, and we're multiplying it by the columns of the second. We're going to use another color, columns of the second. And each resulting element is a product of each of those vectors. So for this first element over here, this top left element here, you can see that it's A11 and A12 element-wise with B11, B21. So it's basically this first row here multiplied by this first column here. And it's kind of doing like an element-wise multiplication, but only within the vector. It takes a good amount of time to like get used to matrix multiplication, but that's basically what's happening with all of the other elements here. Like for this top right one, it's taking the top row here and the right column here, and the same for the bottom ones. I would say not super important to know now, but as you're preparing for interviews, maybe take like a couple hours to just like sit down and do some matrix multiplication just so you get used to like reading matrices and doing the process of multiplication. I've never gotten a multiplication question more than like a 3 by 3 matrix, so use that information how you will. Something to think about, and this is actually a follow-up interview question that I got. Because we're using the rows of the first and the columns of the second, what are some of the shape restrictions that you have to doing matrix multiplication? Something to think about is here in each row, we have 2 elements, and in each column, we have 2 elements. And this is how we're able to come up with this equation here for like one element in our new multiplied matrix. So there are going to be some shape restrictions. There are going to be some matrices that cannot be multiplied together. So let's say A and B are 2 matrices with m by n and p by q, this being their like shape dimension, their dimensions. If we want to multiply these 2 matrices, the way I remember it is that the inside dimensions have to match. So basically, no matter what m and p and q are, n has to be equal to p. If that doesn't match up, then you wouldn't be able to line these elements up together to multiply them together. So I have been asked about the shape restrictions. Basically, m and q can be any number, but n and p have to match in order for matrices to be multiplied. I know there's a lot of information to take in, but any like questions as of right now?
What's a where we'd actually use something like this?
We're actually going to see this matrix multiplication being used in how stats models and a couple other models that you'll get to in like time series. They actually use this in the backend to solve for your coefficients. Okay. You probably will never have to do this as like data science bootcamp grads, but sometimes it's good to know that this is what's happening in the backend. So probably you would not have to do matrix multiplication ever by hand. Probably don't have to do a dot product either. But just good to know. Yeah, it's more of like good to know that this is happening in the backend. You probably won't have to do this for real.
All right, thank you.
You're welcome.
Could you possibly repeat the m times n and p times q, which ones have to match up and which ones don't? Because it wasn't completely clear to me.
Absolutely. So let me just draw it out on these matrices real quick. I think that'll be easier. So here we have, let's say this is A, this is B. The yellow one is A, the orange one is B. So this is M. The number of rows is M. The number of columns is N here. And then for this matrix, P is the number of rows here, and then Q is this number of columns. So N and P have to match. Basically, the number of elements in each row for the first matrix and the number of elements in each column have to match up. Awesome. It is a little confusing especially if you're seeing this for like one of the first times. But I think it's something that it'll start making sense when you try and do some sort of matrix multiplication. But also not the most important thing right now, honestly.
Could you rephrase it as the number of columns in the first matrix has to match the number of rows in the second?
Yes, absolutely. That is correct. Awesome. Oh, sorry, I'm not seeing the chat, but yes, what you have in the chat stands. Well, I'll keep this open. Sweet. All right, let's clear this. So good for us. Python has, our NumPy has built-in functions to do this for us, so we'd never have to do this actually by hand. If you have 2 arrays here, you can use the dot method. So just to show you all the dot method here, we'll do the matrix multiplication automatically for us. And just to show that the order does matter, if we do this is the dot product of A and B. If we do the B, if we do it B and then A, we get a different number. So just important to note that the order of which you're multiplying your matrices matters. If you get more mathy, you might hear like left multiply versus right multiply when you're talking about matrix multiplication. So just good to be aware of. Yeah, furthermore, A times B is not the same as B times A, and also the order in which you're doing your matrix multiplications, if you're doing multiple matrices, also changes the result. Cool. The next type of multiplication is called the cross product, which is not important for our purposes at all. Just good to know. It's also, I think there's like a little snippet of it in the curriculum somewhere. But here we'll just define it for vectors. So the cross product of two vectors is this. It's defined by this equation. You can see that there's a sine function here. There's some n constant. Sorry, n is a vector actually. A and B are the magnitudes. I've broken it down here, but I don't think it's worth going through because we really don't use it in data science at all. But this definition is here for you all. You can't divide matrices. You can't divide vectors, so you cannot divide. However, there something kind of similar to division. There are inverses and also the identity matrix, which are good to be aware of. So we got to talk about inverses and the identity matrix together. So first of all, you cannot divide by matrices, although you can still broadcast element-wise. So let's say you want to divide everything in a vector by 2, you can still do that, but there's no such thing as like matrix division. What we can do is find the inverse of a matrix. And the inverse is sort of like doing like 1/2 would be the inverse of 2. If anyone's familiar with the term reciprocal, that's what that means as well. But every matrix or most matrices have an inverse. When a matrix is multiplied by its own inverse, it results in something called the identity matrix. So one thing to note is when you're multiplying a matrix by its own inverse, the order doesn't matter because it always equals to the identity matrix, whether it's A multiplied by A inverse or A inverse multiplied by A. Doesn't matter for the specific scenario of a matrix and its own inverse. And this identity matrix, what is the identity matrix? Think of it as the operational equivalent of the number 1. When you multiply anything by 1, it is itself, right? So the identity matrix is sort of like the linear algebra version of the number 1. What it looks like is it's a matrix of zeros with ones down the diagonal. If you ever decide to do some matrix multiplication, and if you do it with an identity matrix, you always end up with the same matrix, no matter what order you're doing the multiplication. So it's important to know that the identity matrix is like the number 1. And also the inverse of the matrix is a matrix that when multiplied with itself gives you this identity matrix. Again, everything can be built into NumPy. So here as an example, I have this random array here. NumPy also has an identity method that creates the identity matrix for you. So let me just output all of this. So this is our original matrix. This is our identity matrix that is just numpy.identity. And when I take the dot product of the two, you result in the same matrix. Of course, now it has the float because of like the float data type, but same matrix pretty much. Also, the inverse method exists within NumPy as well. So we can do that. So this is the inverse of our matrix. And then when I take x multiplied by the inverse of x, you end up with this, identity matrix. So you can see, yes, there are some negatives, but it's pretty much a 0, just ones across the diagonal. Cool. I'm also very aware that this is a lot of information. So if all of it is not sinking in, that is absolutely okay. It's kind of like a crash course. This is maybe like 5 weeks of college material condensed into an hour. So don't feel like you have to understand everything of what I'm saying. All right, so that was pretty much all of the basics of linear algebra. And those are things that will kind of come together to build what we kind of need to know about what's happening in the backend of some of our models. Before we get into our actual linear regression, we'll talk about some linear equations and what are even linear equations. I think some of this might seem familiar from like high school algebra classes, maybe, but we'll see. So one of the most common applications of matrix operations is in solving systems of linear equations. So what exactly are linear equations? I think it's important to define explicitly here. Linear equations only have linear variables. So that means all of our unknowns being all of these letters, are only multiplied by a scalar and raised to a power of 1. So that means there's no like squared, there's no like cubed, there's no, I don't know, to the power of, I don't know, like 1/3, for example. So these are both linear equations. Our unknowns here are x and y. So in this case, this is definitely linear because x is not raised to a specific power, and it's also only multiplied by scalars. Here, there's a 2, here is multiplied by 1. This is also a linear equation. I think the other letters kind of throw people off, but e is actually a constant number. I think it's like 2.7 or something like that. Pi is also a constant number. So this also counts as a linear equation. Examples of nonlinear equations, here you can see x squared. Once you have a squared on an unknown, it stops being linear. If you have a log, if anyone, I don't know, oh wait, yeah, you all did log transforms in your project, I think. If you see a log here, immediately not linear. Y to the power of x, that's not linear. This part is linear though. E to the power of x, also not linear. Cool. So this is the part that might seem familiar from like high school algebra, I think maybe. So let's say we have these two equations over here. We have these system of linear equations, x and y, to solve for x and y. One thing we can do is solve it using a matrix method. So first, given these two equations, we need to represent these as matrices / vectors. One way to do it is to take all of the coefficients of the x's and y's and break them out into a matrix like this. So this 1, -2, 3, 2 comes from the coefficients of x and y. So this x is multiplied by 1, you have -2 here, 3 and 2. And this is on one side. We put the x and y like this because when you matrix multiply this out, it'll look just like this. And then we have 1 and 11 on the other side of the equation. And you'll see after you rearrange this, these are actually equivalent representations of these equations. So all of these letters look kind of intimidating. I'm super aware of that. So let's just set these as A and B for now. So let's have this part, the 1, -2, 3, 2, be A, and then this be our B. Let's run this for now. Basically what our equation looks like with this as A, this as B, this is what we have. And if we remember from algebra, when we want to solve for our x and y, we want to isolate it on one side of the equal sign. So this is what we're going to try and do. So given this, how can we move our A over to the B side? Or how can we just isolate x on one side? In normal algebra, we would do a division, but we can't divide matrices. So therefore, we make use of the inverse. So what we're doing here is we're going to left multiply the inverse to both sides of the equation. And we're doing that because we know that once we have this left multiply of the inverse of A over here, it turns it into the identity matrix, which is like the number 1. So that's where this equation comes about. So we're multiplying inverse of A on both sides. And important to remember that we're left multiplying. So we always put the inverse of A to the left of whatever is existing. And then we solve for this. So basically, this comes back to x being equal to the inverse of A multiplied by B, which is great because we can find out all of these things through some quick Python code. So I have our A and B here. I have our inverse of A here. So here I'm taking the inverse of A. And I'm just going to take the dot product of the inverse of A and B. And with this, it solves our equations immediately to get 3 and 1. What this means is x is 3, y is 1. Let's just go and look at our equations one more time to just confirm that that makes sense. X is 3 and y is 1. So 3 minus 2 is 1. 3 by 3, that's 9, plus 2 is 11. So that checks out. So rather than substituting, and I forget all those other techniques of solving equations, we can do it the matrix way. And this becomes even more important when you have more and more equations and more unknown values. It becomes much easier to do it the matrix way versus trying to do it by like substituting everything here and there. Now, next we're going to get into how this connects with our OLS. Any questions at this point? Cool. All right, so let's talk about how this relates to our OLS and how we can think about the data frames that we have as like vectors or matrices. So lots of words here, but we're going to walk through it. A linear regression can be interpreted as the solution to a system of linear equations. So basically, each observation is a linear equation, and the coefficients are the linear unknowns that we're solving for. So one thing to remember is that each observation is a linear combination of features. So let me actually take this example. This is just one of the car data sets. Oh no, this does not work. Huh, okay, hold on. I have this somewhere. Let me just really quickly put this data frame in. Sorry about that. It has been a little while since I've run this notebook. Right, this goes here. All right, so this, I'm going to change this real quick to, does this work now? Sweet. Okay, so we have our data frame. So let's just say in this data frame, what we're trying to predict for our Y variable here is miles per gallon. I don't know cars that well, so I don't know if this makes sense, but let's say we're trying to predict miles per gallon with all of these other features. With this, we can actually represent each observation as a linear equation. So in the same form that we had this before, we'll just say that, all right, 18 miles per gallon is equal to 8 cylinders, 307 displacement, 130 horsepower, blah, blah, blah. So it's some linear combination of all of these features. And what we're trying to solve for is, all right, on average, if we want to predict miles per gallon, what are the coefficients that go with these numbers that make sense for a prediction for miles per gallon? Does that make sense? I feel like that was not a good English sentence, but okay, good, I got the point across. So our prediction equation, so if you remember from your phase 2 projects, at the end, when you get all of those coefficients, the way that you use those coefficients is in an equation that looks like this. So you have your constant plus your coefficient for some variable multiplied by the variable value. So betas are going to be our coefficients, and then your x's are going to be whatever the value is. And so this is what that equation looks like. So in matrix form, we're going to have y equals to x multiplied by b. I mean, the letter can always change, but in this case, let's just use b because it looks like beta. So this is how we can solve or represent our data frame as like matrices. So something to just remember is that, yeah, we're solving for b. And each of these is a linear equation that we're going to solve. So cool. We can set it up the same way that we set up our linear equations earlier. Let's have our x and our y. So let me just, I think this might be slightly different. Okay, so there's no year here, so it's model year. Okay, there we go. So this is our x, and then we're going to have a constant term. This, I actually linked a couple articles as to why we have to do this, but this is just a constant term. So this is what our x looks like, just so that you can get some coefficient for your intercept. And then, as we remember, we're gonna have to take the inverse of this to help us solve for b. So yeah, let's try and do x inverse. So if I run this cell, you actually see that we run into an error. And that error makes sense that it's there because it says here that the last 2 dimensions of the array must be square, which sucks because this is the equation that we use to solve our system of linear equations from before. Why doesn't it work for our data frame now? It goes into pretty deep linear algebra theory, but the important thing to know is that we can only calculate inverses of square matrices. That is just a fact of matrices and like linear algebra theory. So this is kind of difficult for us now because we have like 1, 2, 3, 4, 5, 6, 7 columns, and we don't want to just solve for like 7 rows. That's like using 7 data points to form a linear regression, which is not going to be very helpful. So what else can we do? This is just some linear algebra theory. What can we do? How can we make what data that we have into a square and somehow solve for B? I don't have all of the equation out here, but I'm going to walk through it real quick. We are actually going to make use of the transpose. So that's why the transpose I brought up towards the start of this study group, but we're going to have to make use of the transpose. And this is the equation that we're going to use. And I'm actually going to just draw it out here since it's not in this notebook. So what we started with was we had y equals to x times b. And we know that we wanted to solve for x. However, x wasn't a square, so therefore we couldn't take the inverse of x. What we can do to make it square is actually multiply it by its own transpose. So by doing that, you would left multiply the transpose, so x transpose times y, and do that on both sides equals to x transpose x multiplied by b. When you multiply a matrix by its own transpose, it ends up being a square. I won't get into why that is right now, but if you break down the matrix multiplication, it comes to that x transpose times x, or anything times its own transpose, whether it's left or right multiplied, it becomes a square, which is pretty neat for our purposes. So we're kind of going to compound a bunch of things that we've learned. You can actually find the inverse of this entire product. So because this is now a square, we can find the inverse of x transpose x. So what we're going to do now is we're going to take x transpose x inverse on both sides and then multiply. And let's just draw this real quick. I will say ever since teaching at this job, I've been really good at or infinitely better at drawing with my mouse. So let's see, x transpose x, b. There we go. So now we're at this stage. What's really neat here is if we remember the inverse of anything will pretty much cancel each other out and become 1. So these all cancel out and we end up with this equation, which is what I have over here. So it was a bit of a process of getting there. And the equation is now a little bit longer than the one that we had before. But now we have an equation that we can solve for all of the coefficients just using matrices. And we're really just using the X matrix that we had before. So let's apply this real quick. Let me just erase this square here. What I have defined here in multiple lines, I have our X transpose. I have X transpose X, which is this part here. And then I'm basically solving the equation and I have my values for B. So these are all of my B values. Let me clear all this for now. So these B values, the way that this works is they correspond to each of the columns in your X data frame in that order. So let's zip together the columns and the coefficient values. So these are our values here. For now, we are not doing any model tuning. We're just going to see how it solves the equation. And really, really quick, what we're going to do here is we're going to compare these coefficients to what we get out of scikit-learn. You could also do this with stats models, but they'll come up very similar. So what I'm doing here, I'm just quickly instantiating a linear regression. I don't need that constant column that I created earlier, and I'm going to sit and look at our intercept and coefficients. So this is going to run for a little bit. Shouldn't take this long. Okay, good. And I have my constant and coefficients. So let's compare here. So you can see here our constant is negative 14.5, which matches this. And all of our coefficients here, you have the the powers, so it's a little hard to read, but you can see here should be 0.329 matches 0.329. The displacement 767 matches 767. So we're basically solving all of linear regression with linear algebra and matrix multiplication, which again, I think is important to reiterate. You're not going to do it this way, but good to know that it is a method. If you ever run into errors with stats models libraries that say that you cannot invert a matrix or something about like answer doesn't converge, because you will be using stats models later in like time series section, it's because the matrix multiplication doesn't work. And in some scenarios, yeah, there's something to do with the matrix multiplication. So if you ever see errors that come up talking about like the invertibility of a matrix, it's because they're trying to do some matrix multiplication that doesn't work out. So yeah, just good background knowledge to know. Cool. And that's pretty much it for linear algebra. I've linked a bunch of resources. This was a good one. I actually had no idea how to interpret like X transpose times X. It's pretty interesting. It talks about like, it has something to do with like the correlation of your variables. So it brings back like multicollinearity, which you all talked about as your assumptions. This is a really good video series by 3 Blue 1 Brown on linear algebra. From my former students, they like to just watch this before they start their interviewing phase, just so that they have those like terminology words in their head. And yeah, just some other resources I've linked here. But cool, that's all I had to share for you all. Any questions? Of course, feel free to reach out to me on Slack. I'm always on Slack. If you have any questions about this, you want to talk about anything?
I have a question, please.
Matthew? Oh, yeah.
Where I can find this notebook in your repo?
Oh, yes. So I linked my repo to your Slack channel earlier today. So you can find it there. I think, yeah, I linked, let me just double check that I have that there. Let's see. Yeah, oops, that's my own Zoom link. Cancel this. I linked this here. So here is the same notebook. Everything's already run, so you can take a look. Feel free to clone the repo. This is the repo for my cohort that's about to graduate. So all the materials are there. We just want to like look and see like additional notebooks. They're all there. So feel free to peruse as you wish.
Thank you.
You're welcome. Anything else? Cool. I think I really want to reiterate that it's very unlikely that you'll be doing like actual linear algebra theory while you're doing like data science or machine learning. It's just that a lot of this math is embedded into a lot of the models that you will be using. So you'll kind of be using them, but not directly. And depending on like the kind of roles that you're going to be going for in the future, if you want something that's more technical or you're going to be like writing algorithms eventually in the future, this will be really good to know. But for most students who are graduating for their capstone project, you don't need to know true linear algebra theory. Sweet. Well, it's been awesome. Claude, I don't know if you have anything to add. Nothing? All right. Well, I know that you all have an additional study group / office hour at 4 Eastern. Is that right? So go to that, build the deck of cards, and yeah, feel free to reach out to me on Slack. If anyone wants to talk about anything math related and like how much math you need to know to do whatever, I love that stuff. So feel free to reach out. Well, it has been a pleasure. I hope to see you all sometime soon. And yeah, linear algebra. Bye, everybody.
Appreciate it.
Thanks.
Thank you.